All right, it's time for day 3 of our week of review and synthesis. But before we get to the review, I just want to give you some congratulations. You have made it to the end of the Physics 122 course, and this is a difficult technical subject, and you have stayed strong, and you have stayed the course, and you have done well, and you have learned a lot. You've achieved something. And I think sometimes at the end of the semester, all we feel is relief. But I want you to just pause for a minute and reflect on the fact that you have achieved something. You have learned a lot more about the world. You know more about physics than most people in the world now, than nearly all the people in the world now, which is kind of crazy. You know a lot more than you did at the start of the semester. It is a moment that is worthy of congratulations. I would say too, whenever you reach these transitional moments, I just want you to pause for a minute and savor it. We're too eager to just get on to the next thing. But just pause for a minute and say, I did this semester, I learned this material, I've done well. I've had some interesting experiences along the way. Savor that moment as you're looking back. Think about all the things that you've done, all the things that you've learned. Congratulate yourself. And just take a minute to savor this moment. And now it's time for the review. And so today we're going to do exam scenarios. This week what I am doing is I'm looking at kind of like interesting things in the world and saying like, what is something cool that the physics that we've learned can explain? And I'm writing exam scenarios based on it. And we're going to see a bunch of past exam scenarios that I've written. Now your exam is going to have a slightly different structure. There won't be multiple choice. There will just be short answer questions for you to work on. It'll be a lot like the structure of exam 2, okay? So slightly different structure, but the same basic overall philosophy. I'm just looking at the world, cool things in the world that physics can explain. And I want you to check out on Canvas the full details of exam number 3 and how that is going to go down. But before we get into the review, I just want to do a couple quick announcements. First off, if you have any questions about your grade, send me an email. Don't send me a message on Canvas. Send me an email and we will get to the bottom of it, because another thing I'm going to do during final exam week is start to put together course grades. Another thing I want you to do is I want you to give me some feedback. Now here's the thing. I always give a survey every year, and the survey that I give is actually more valuable to me than the standard university administered survey, because I want to get into the weeds of what really worked for you folks, okay? And I have very specific questions that I want to ask you. So I'm going to post a survey on Canvas, and it's going to be available on May 8th. So it's going to be available starting on the last day of class. And I want you to complete it through May 18th, and I will send you announcements about this. And it's going to be different than in previous years, because in previous years, I asked about the most effective of the in-person elements of the course. What I want to do now is I want to ask you questions about the online instruction that we've been doing. I want to ask you what was effective, what was not, what suggestions do you have for me? Because right now I am actively thinking about next fall. And as you know, CSU is looking at different models for the fall. And we might be back in person and we might be doing business as usual. We might be wholly online, or it might be something in between. My best guess is something in between. So I want to think about what are the pieces that are working well online? What are pieces that, not to put a fine point on it, but kind of suck online? And so what are the pieces that we have to prioritize if we're looking at doing face-to-face instruction? That's the feedback that I need from you folks this semester. I also want to mention too, I'm going to give some details about this. I always finish the semester by having a post-exam reception, and we can't do it in person this year. I so wanted to be able to have everybody over to the house, but instead what I'm going to do is Carol and Milo and I are going to sit in front of the computer and we're going to Zoom it up with you guys. And so if you want to like take a window into our home and you want to say hi to Carol and Brian and Milo and just kind of celebrate the end of the semester, we will happily do that with you. And Carol is excited about it, and Milo's a little skeptical. He does not like glowing screens, but he'll be there and he'll probably insert himself into the picture at some point. Details forthcoming. So today our practice is going to be exam scenarios, and what I'm going to do is I'm going to put one up. I want you to pause and I want you to think about it. And then I really want you to pause and I want you to try that exam scenario. And I'm not going to go, I'm going to give you details as to how to get started on them, and I'm going to post the full details so that you can look through them at your leisure. Now here's the first question I want to ask you. And this relates to an exam scenario we're going to see in a minute. Cherenkov radiation happens when I have particles that are moving faster than the speed of light in a material, and I can have particles moving faster than the speed of light in a material because remember, in a material, the speed of light is this canonical value for the speed of light, the 3 times 10 to the 8th meters per second, divided by the index of refraction. So if I'm looking at glass, which has an index of refraction of about 1.5, the speed of light in glass is about 2.0 times 10 to the 8th meters per second. And I can have an electron moving faster than that in glass. It can't move faster than this speed because that is the ultimate speed limit for the universe. That would violate all kinds of laws of physics. But you can certainly have them moving faster than the speed of light in a medium. And if I have a charged particle moving faster than the speed of light in a medium, and it gives off Cherenkov radiation. And the Cherenkov radiation, I want you to, this is Cherenkov radiation around a nuclear reactor. The intensity varies with frequency. I want you to look at this picture and say, is the intensity proportional to 1 over the frequency or proportional to the frequency? Which one is it? Look at the picture, look at the color. That's your cue. I'll be back. And of course, the light that you're seeing is bluish. Okay, so and if we're seeing blue light, what that's telling me, I have more intensity at higher frequencies. And so the intensity I would expect is just going to be proportional to the frequency. And in fact, that's approximately true. The intensity is basically proportional to the frequency. And that relates to our first scenario. So here's our first question. And I see there's a typo in here. This should actually read 50 kV. Okay. It's possible for an object to travel faster than light, as we've seen. So we have, and we're told about that, and this is like the Cherenkov light thing. So then a question asks, an X-ray machine creates high-energy photons by accelerating an electron through a metal target. A typical clinical machine accelerates electrons through a voltage of 50 kilovolts. 2 questions. With this accelerating voltage, what is the shortest wavelength? And then B, if I shot those electrons at water, would they produce Cherenkov radiation? Think about it, Think about how you'll start this problem. I'll be back. Well, if I've accelerated them through a voltage of 50 kilovolts, that means the electrons accumulate a kinetic energy of 50 electron volts. And so the shortest wave, that's the highest energy the photon can have. The highest energy the photon can have would be 50 electron volts. And knowing that energy, I could calculate a wavelength. But the other thing I could do is I could say, I'm going to take this electron and I'm going to shoot it into water. And if the kinetic energy is 50 electron volts, so the kinetic energy is also 1/2 mv squared, I could calculate what the speed is. And then I would see, would they produce Cherenkov radiation? Well, if they have Cherenkov radiation, the speed of the particles has to be greater than the speed of light in the medium, which is equal to c divided by the index of refraction. So we're asking this question, is the speed of the particles greater than the speed of light in the medium? That's the question you're trying to answer. I'm going to go ahead and show you briefly the solution. That will be posted, and then I want you to remind yourself of those details and go back and review that at your leisure. Next question that has to do with the rear windshield kind of like thing. You have one of these things in the back of your car, you know you do, and you put a current through it and it melts ice and frost on your window. So go ahead and read this one through. Think about how you'll answer those questions. I'll be back. Okay, so let's think about the crucial details. This thing is working like a series of resistors. And what it looks to me is that there's a bunch of resistors hooked up in parallel. because each one of the wires has a certain resistance. And so it's a combination of parallel resistors. Okay, that's what it's looking like to me. And they hook them up to a 12-volt power supply. And when it's first turned on, the resistance to the grid is 0.5 ohms. I'm connecting it to a 12-volt battery. So what power should I have? Well, remember, we have various expressions for computing the power in electrical circuits. So I want you to complete that calculation. Second question, and this is kind of like related to, we had a dog of a relative who was in our car and was scratching the back windows, little scamp, and then broke 2 of the wires. And when the dog broke 2 of the wires, that changed the electrical nature of the system. Question, if you broke 2 of the wires, what would that imply about the resistance of the grid? I want you to think about how you would do that. Remind yourself of the details of parallel resistances. And when you're ready, take a look at the posted solution. Now let's take a look at this scenario. This is one about electrophoresis. So go ahead and read this one through. And this is just the problem. This is basically the setup for the scenario. Read it through. Think about what's happening physically. And if it's me, I'm doing this. I'm saying like, okay, positive side of the power supply is here. That's my positives. I'm going to have an electric field that goes from the high potential to the low potential. So electric field is going in this direction. Positive charges are going to experience a force in that direction. I'm thinking about that. Okay. And also, too, it looks like they're talking about heating the gel. So it sounds like I might be wanting to think about this as like, oh, I've put a voltage across this gel, and I'm thinking of the gel as a resistor. And I remember the resistance of a resistor depends upon its dimensions. So those are some different ways to think about it. So keep wrapping your mind around this one. Don't jump ahead to the question. Keep wrapping your mind around it. Make sure you understand what the setup is, what is happening physically. When you're ready, go to the questions. And the first questions are here, the direction of the electric field and the direction the fragments move. Well, that has to do with the charge on the fragments, of course. And the maximum recommended electric field is 500 volts per meter. What does that imply about the power supply voltage? Well, remember, we know something about the relationship between the electric field and the potential difference. Remind yourself of that to complete that calculation. And then for the short answer question, we are in fact asked to think about the gel as a resistor. So this is going to have to do, we're going to compute a current and a power. We're going to be treating the gel inside here as a resistor. So remember the basic properties of resistors, and the resistance is related to the dimensions and to the resistivity, blah, blah, blah. Remember all that and work your way through this problem right here. And I want you to complete your calculations and think about it, assess your result before you move on to checking out the solution. And here is the solution, and this will, of course, be posted with the others. First the multiple choice, then the short answer. Now let's take a look at the next scenario. And this has to do with scanners that used to be used by TSA, and they used to employ low energy X-rays. Okay? And then there's some questions about those low energy X-rays. So I want you to read it through, make sure you understand what the situation is. Think about the questions. Work your way through this one. I'll be back. Okay, so we're given the wavelength of the X-rays. Well, the wavelength is going to be related to the energy, and we can use the basic energy relationship we've used previously, that the energy is just equal to 1240 divided by the wavelength in nanometers, wavelength in electron volts, wavelength in nanometers. With that in hand, I can figure out the kinetic energy, or the energy of the photons. And if I have, like, for instance, a 40 kilo electron volt photon, the voltage the electron needs to be accelerated through is 50 is 40 kilovolts. So remember that relationship. Think about the next piece. If I want to increase the intensity of the X-rays, but I don't want to change their wavelength. And remember, one of our basic rules was I have one electron gives rise to one photon. So if I want more X-rays, I need more electrons. But if I want them to have the same wavelength, they need to have the same energy. So think about what that means in terms of the answers that are given. The short answer question is one, and I want you to think about this. I want you to read it through. This is one that is intended to be kind of very, very open-ended. Explain the nature of the, like now, they use microwaves to probe people. They used to use X-rays. In both cases, you're exposing people to what's called radiation, but they have very, very different effects on the body. So why is exposure to X-rays more of a concern than exposure to microwaves? It's a very open-ended question. I want you to think about that. Remember everything we've learned about those different kinds of electromagnetic waves. Cogitate and take some time to think it through before you look at the posted solution. And this solution, like the others, will be posted for you to take a look at. Next up, this has, let's see, a couple of questions that have to do with the photon model of light, but they're two different physical situations not directly related. I don't usually do that, but we'll have like this problem right here and this problem right here are two different problems. So I want you to work them through separately. Think about them, read them through, think about how you're going to answer them. I'll be back. Now, if the cathode has a 2.3 electron volt work function, okay, that's the amount of energy that it costs to liberate an electron from the surface. So if light comes in and hits the surface and it's going to pop an electron out, the minimum energy that the photon has to have is 2.3 electron volts. That's the cost. And given that energy, I can calculate the photon wavelength. If you decrease the wavelength of the light, that increases the energy of the photons. But the intensity is being held constant. So this is the same amount of energy, but the energy per photon is increased. What does that imply about the number of photons? So think about that, and then also think about this. We have this rule that basically one photon gives rise to one electron. So think about the number of photons. Think about what that says about the current. So keep working that one through. And now we're going to turn and think about this one right here. Okay, so this is pulses from a laser. They're going to be used to treat a port wine birthmark. And you're given some details about the pulse of laser light. How are you going to solve that one? Think about that one. I'll be back. Well, we're told the wavelength of the laser. I can use that to figure out the energy of individual photons, okay? And I'm also told the energy of the pulse, and I'm given the duration. The power, remember, there's a relationship between power and energy and time that's this. The power delivered is the energy delivered divided by the time in which it's delivered. Oh, and then power is also related to intensity. Remember how the power versus intensity thing kind of like comes out. So remind yourself of all those details. Work your way through the solution before you check it. And this solution, like all the rest, will be posted. One more scenario, and this was a fairly ambitious scenario that I posted a few years ago. And this has to do with like dating water. So I want you to take a moment, read this one through, think about how you'll solve it. I'll be back. So the first question is basically a half-life question. That's just basically a half-life question. We know in a typical sample of water, about the fraction that's chlorine-36 is about 7 times 10 to the minus 13th. And so we can use that to date water, just like carbon-14 can be used to date artifacts. So I want you to remind yourself of the details of carbon-14 dating, and then apply that to this problem right here. The next piece, oh heavens to Betsy, that's a question about the motion of charged particles in magnetic fields. So that's one that you're going to have to think about and remind yourself of those details. The short answer question is a question about the decay. So it's a decay of the chlorine-36. Now think about this. Okay, chlorine-36 is a beta minus emitter. So it's giving off an electron, okay? And I can figure out the equation for the decay, what 36 chlorine turns into. I can go ahead and figure that out. And it's going to turn into a daughter nucleus plus an electron. So there's a daughter nucleus you have to work out plus the electron. The mass of the things over here on the left is greater than the mass of the stuff on the right. Mass is lost during this reaction. And the reason why mass is lost is because energy is lost, and there's this equivalence between mass and energy. And the lost energy basically goes into the kinetic energy of the electron. So what you're going to do is you're going to figure out how much mass is lost and going from here to here. Convert that into energy. That energy is the kinetic energy. That will let you get the speed of the particle. There's a lot of steps in that problem, but working through it is kind of a good way to remind yourself of those details. So work that one through before you check the posted solution. And now I just want to take a couple of minutes to do some closure with the class. And typically what I would do on the last day of class, it would be the last time that we're together as a class. And for many of you, you're graduating. And so it's not just the last time I'm going to see you in Physics 122, it's the last time I'm going to see you at Colorado State University. And at moments like that, I just want to pause and think back. First off, I just want to say thanks. I have a very privileged existence. I love what I do. And the reason I love what I do is because of the people that I get a chance to do it with. You folks have been a remarkable class. I'm sorry that our semester ended this way, but I'm glad that before we went online, I got a chance to know some of you and interact with you and get to know you a little bit. It has been a blessing. Thank you so much for the chance to be your instructor. And I want to pause and say congratulations. You folks have done something amazing. By finishing this physics course, you've done something amazing. And some of you are graduating. You have completed 4 or more than 4 years of intense instruction where you've learned a lot, you've worked hard, you've had to stretch yourself, you've had to challenge yourself. You have done something amazing. About 5% of people in the world get a college degree, 1 in 20, and you are part of that 1 in 20. You have achieved something truly remarkable. Take a minute and pause and give yourself a pat on the back. Congratulations. And I want to say farewell. I want to say farewell to the class. I want to just pause and say goodbye. Thank you. Thank you for this. Wherever life takes you next, pause to enjoy the journey. And this is one of the things I love most about Milo. He reminds me, when you are hiking and you're looking at the clouds and you're smelling the flowers, you just pause and enjoy that moment. Savor that moment. And whatever you're doing, enjoy it. Take the time to kind of just live in the moment and enjoy that moment. Milo helps remind me of that, and I'm helping remind you of that very same thing. And finally, be well, do well, and keep in touch. Wherever life takes you next, drop me a note and say, like, hey, Brian, just FYI, here's what I'm doing. And whatever you're doing, I just want to know, what is the next chapter in your story? I've learned to like you folks. I care about you, and I want to know what happens next. And finally, just thanks for the chance to be able to share my story. I'm not going to say anything else, because even just sitting here and thinking about you folks and everything that we've shared this semester, everything that this has meant to me, I will start to cry. So I'm just going to stop right now. And thank you so much for everything. Be well, do well, keep in touch. Take care.